Tonight, we're going to travel together through the slowest, most patient story ever told, the story written in stone beneath your feet. Close your eyes, and let yourself sink into the comfortable knowledge that while everything around us rushes and changes, the earth beneath us moves in rhythms so slow, so steady, that they transform anxiety into wonder. Let me tell you about the heartbeat of our planet. Deep below the surface, beneath continents and oceans, the earth breathes. But this breath is so slow that a single inhale takes millions of years. The rocks that form the floor of the ocean basins, those dark, dense stones called basalt, are born at underwater mountain ranges we call mid-ocean ridges. Here, in the deepest darkness of the sea, melted rock wells up gently from the Earth's mantle, cooling into new oceanic crust at a pace of just 2 to 5 centimeters per year. About the speed your fingernails grow. Imagine that, the entire floor of the Atlantic Ocean was created at the pace of a fingernail, slowly, patiently, over hundreds of millions of years. This process has a beautiful name, seafloor spreading. And as this new rock forms and gradually pushes outward from these underwater ridges, it carries with it a secret. When the molten rock cools, tiny magnetic minerals within it align themselves with Earth's magnetic field, like countless microscopic compass needles frozen in time. They become a permanent record, a memory locked in stone. And here's what makes this so wonderfully peaceful to contemplate: Earth's magnetic field flips, north becoming south and south becoming north, every few 100,000 years. These reversals create stripes in the ocean floor, alternating bands of normal and reversed magnetic polarity, spreading outward symmetrically from the ridge like the most patient barcode ever written. Scientists discovered these patterns in the 1960s, and in doing so, found proof that continents drift, that ocean floors spread, that our planet is constantly renewing itself in the slowest of dances. Now, let's follow one of these newborn rocks on its journey. As it moves away from the mid-ocean ridge, carried along by the conveyor belt of seafloor spreading, something wonderful happens in the water above it. Fine particles, the remains of tiny marine organisms, flecks of clay, cosmic dust from space, begin to drift down like the gentlest snow. This sediment accumulates grain by grain, so slowly that it would take 1,000 years to build a layer the thickness of a sheet of paper. There's something deeply soothing about this pace. While we rush through our days, the ocean floor receives its blanket of sediment in a rhythm unchanged for billions of years, particle after particle, settling through the quiet water, building stone from whispers. These sediments, over time, compact and cement together, transforming into sedimentary rock. And sedimentary rocks hold perhaps the most calming secret of all: they are patient historians. Each layer represents a moment in Earth's vast story, a moment that might span thousands or millions of years, but a moment nonetheless. Limestone, that pale, soft rock, forms primarily from the accumulated shells and skeletons of marine organisms. The white cliffs of Dover, those iconic chalky faces overlooking the English Channel, are made almost entirely of the microscopic plates of ancient algae called coccolithophores. Billions upon billions of these tiny organisms lived, died, and drifted to the seafloor over millions of years during the Cretaceous period, when dinosaurs still walked the earth. Their remains compressed into rock so gradually that the process itself is almost unimaginable, pressure upon pressure, year after year, until the soft ooze of the sea bottom became the solid stone of cliffsides. Time turned to stone. Death turned to beauty. And so our first chapter closes with this thought: beneath us, around us, the Earth is always slowly writing its story in layers, in magnetic stripes, in the patient accumulation of tiny shells. Nothing rushes. Nothing forces. Everything simply becomes, in time. Rest now, and let yourself become part of that same patient transformation, tension slowly settling, thoughts gently drifting down like sediment through dark water, until you, too, find yourself peaceful and still. Now that we've followed the ocean floor on its outward journey, let's discover where it goes when its travels are complete. Because nothing in geology is truly lost, everything transforms, everything returns, everything cycles in the most peaceful of rhythms. Our oceanic crust, now perhaps 100 million years old, dense and cool, continues its slow drift across the Earth's surface. Eventually, after traveling thousands of kilometers at that same fingernail pace, it meets something immovable, a continent. And here, something beautiful happens. The oceanic crust, being denser and heavier than the lighter continental rock, begins to slide beneath the continent in a process called subduction. It's as if the ocean floor is politely bowing, curving downward, descending back into the Earth's warm interior from which it came. This is geology's way of recycling, the subduction zone, where old seafloor returns to the mantle, completing a journey that might have lasted 200 million years. Picture this descent. The oceanic plate slides beneath the continent at an angle, moving down into increasing pressure and heat. At first, it remains solid, cold and rigid from its time near the surface. But as it sinks deeper, 10 kilometers, 20, 50, 100, the temperature rises. The rocks begin to release water that had been locked within minerals since those sediments settled on the seafloor so long ago. This water rises into the hot mantle rock above, and something almost magical occurs. The addition of water lowers the melting point of the rock, and portions of the mantle begin to melt, forming pockets of magma. This magma, being lighter than the surrounding solid rock, begins to rise, ascending slowly through the dense continental crust above like bubbles rising through honey. Most of this magma never reaches the surface. Instead, it cools within the crust, forming massive bodies of igneous rock called plutons. These underground chambers of crystallizing rock cool so slowly, sometimes taking millions of years for a single pluton to solidify completely, that the minerals within them have time to grow into beautiful, interlocking crystals. This is how granite forms, that speckled stone of countertops and mountains. Each crystal, the glassy quartz, the pink feldspar, the black mica, grew peacefully in the dark, molecule by molecule, as the magma cooled by fractions of a degree over millennia. There's something profoundly restful in imagining this process, deep underground, in total darkness, perfect crystals forming with such patience that each one might take thousands of years to grow to the size of your thumbnail. But some of that magma does reach the surface, and when it does, we call it a volcano. Yet even here, in what we think of as geology's most dramatic moments, there is often a slower story. Not all volcanoes explode. In places like Hawaii, far from subduction zones, magma rises from deep mantle plumes, stationary hot spots that persist for tens of millions of years. The lava that emerges from Hawaiian volcanoes is thin and fluid, flowing downslope in rivers of molten rock that move with an almost lazy grace. You could, in many cases, walk away from a Hawaiian lava flow. It advances at the pace of a slow walk, giving the land time to prepare, time to accept this gift of new rock. And when this lava cools, it forms more basalt, the same rock that forms the ocean floor, completing the circle. Here's a thought to carry you deeper into rest. The Hawaiian Islands themselves are a timeline you can see. Each island is a volcano, and each volcano formed as the Pacific plate slowly drifted over the same stationary hot spot deep in the mantle. The Big Island, Hawaii, sits over the hot spot now and is still growing, still active. Moving northwest, each island is progressively older, Maui, then Molokai, Oahu, Kauai, each one marking a moment when that spot on the Pacific plate sat over the hot spot, received its volcano, and then drifted on. Kauai is about 5 million years old. The Big Island is less than 500,000. The hot spot has remained almost perfectly still while the plate above it has traveled thousands of kilometers. It's a calendar written in islands, a clock that ticks once every million years, measuring time in mountains. And what happens to these volcanic mountains, these islands? The moment they emerge from the sea, another process begins, one even more patient than their formation. Rain falls. Waves crash. Minerals dissolve. Plants take root in cracks, and their roots slowly pry the rock apart. This is weathering and erosion, the gentle dismantling of mountains, the return of rock to sediment. A granite mountain, thrust up by tectonic forces, might take tens of millions of years to wear down to sea level. But grain by grain, the rock becomes sand, the sand becomes soil, and that soil washes into rivers that carry it back to the sea, where it settles, once again, to the ocean floor. The cycle completes. Ocean floor to sediment. Sediment to rock. Rock into the depths. Depths to magma. Magma to mountain. Mountain to sand. Sand to sea. Around and around, nothing wasted, nothing lost, everything transformed in time so vast it makes all worries seem small. Let yourself drift with this knowledge. You are made of the same atoms that have cycled through this process countless times. The calcium in your bones may have once been limestone on an ancient seafloor. The iron in your blood may have crystallized in a cooling Pluton deep underground. You are stone and water, cycling, returning, always becoming. Rest now in this great cycle. Let your thoughts erode like mountains. Let yourself settle like sediment through dark water. Let's descend now, gently, into the crust beneath our feet and discover the shapes that time creates in stone. Because rocks don't just sit still in neat, flat layers, they bend, they fold, they flow like thick honey over millions of years, creating architecture so grand and so patient that witnessing it brings a peculiar peace. Imagine a layer of sedimentary rock, perhaps limestone, lying flat on an ancient seabed. Over millions of years, sediment accumulates above it, layer upon layer, the weight building slowly, compressing what lies beneath. Then, tectonic forces begin to push. Perhaps two continents are drifting toward one another, or an oceanic plate is subducting beneath a continental margin. The compression builds, not suddenly, but over tens of millions of years. And here's what's remarkable: rock, that symbol of permanence and rigidity, begins to bend. This is called folding, and it happens because at the timescales and temperatures and pressures deep in the Earth's crust, rock behaves not as a brittle solid but as a ductile material. The layers curve upward into arches called anticlines, and downward into troughs called synclines. If you've ever seen sedimentary layers exposed in a road cut, tilted at steep angles or curving in great waves, you've witnessed this process: stone flowing like fabric, creasing and folding under pressure so gradual that the crystals themselves have time to shift and rearrange without breaking. A fold that appears frozen in the rock face may have taken 20 million years to form, bending at a rate too slow to measure in human lifetimes, too slow to perceive, yet inevitable as breath. In mountain ranges like the Appalachians, you can see these folds stretching for hundreds of kilometers, parallel ridges and valleys that mark the crests of anticlines and the troughs of synclines, a landscape of frozen waves created when Africa collided with North America 300 million years ago. Stand in those mountains, and you're standing in the wrinkles of an ancient collision, a crash that unfolded over millions of years at the speed of growing fingernails. The violence happened so slowly it was gentle. The catastrophe took so long it was peaceful. But not all rock folds. Sometimes, when the pressure is too great or the rock too brittle or too close to the surface where it's cold, the stone breaks instead. These breaks are called faults, and they too have a calming story to tell. When rock fractures along a fault, the two sides slide past each other, sometimes suddenly in an earthquake, yes, but more often in a process called fault creep, where the movement happens so gradually, so smoothly, that no earthquake occurs at all. The rock simply slides, millimeter by millimeter, releasing its tension without drama. Along California's Hayward Fault, you can see curbs that are slowly offset, buildings whose foundations have shifted centimeters apart over decades. The earth is moving, adjusting, finding balance, and most of the time it does so without anyone noticing. Here's a thought that brings profound rest: the stress in rock accumulates so slowly and is released so regularly that most of the Earth's tectonic motion happens in silence. The plates drift, the mountains rise, the faults slip, and the vast majority of this movement is imperceptible, peaceful, constant. The Earth is always adjusting itself, always finding equilibrium, always releasing tension before it builds too high. Now let's visit one of geology's most meditative features, the unconformity. An unconformity is a gap in the rock record, a missing chapter in stone. Imagine layers of sedimentary rock accumulating on a seafloor for millions of years. Then the sea level drops, or the land rises, slowly, of course, over millions more years, and these rocks find themselves above water. Exposed to air and rain, they begin to erode. Millions of years pass. Valleys are carved. Hills wear down. Then, eventually, the land sinks again or the sea rises, and new sediment begins to accumulate on top of the eroded surface. When this happens, geologists later find newer rock layers sitting directly on much older layers, with millions or even hundreds of millions of years simply absent, eroded away and lost. The boundary between these layers is called an unconformity, and it represents time itself, made visible as absence. James Hutton, the Scottish geologist often called the father of modern geology, stood at one such unconformity at Sitkar Point in Scotland in 1788. Below him were vertical layers of ancient rock that had been deposited horizontally, then tilted and uplifted and eroded. Above these, lying at an angle, were younger horizontal layers. Between them, a gap representing perhaps 60 million years. Hutton realized in that moment that the Earth was far, far older than anyone had imagined, so old that entire mountain ranges could rise and be worn completely away, with new layers accumulating on their eroded stumps, and this cycle could repeat again and again. He was looking at what he called deep time, time so vast that human history is barely a whisper at its end. There's something beautifully humbling about unconformities. They remind us that even stone is temporary. Even mountains are just moments. The mightiest peaks will one day be sand. The deepest valleys will fill and be buried and forgotten. Everything changes, but the change is so slow, so measured, that from our perspective it appears as stillness. In this, there is comfort. Your worries, your anxieties, your troubles, they too are small against this vastness. They too will erode, will be weathered away, will become something softer with time. Picture yourself now as a layer of sediment, settling slowly through clear water. The weight of your day, the pressure of your thoughts, gradually compressing you into something more solid, more peaceful. And if there are gaps in your memory of today, if some moments have already eroded away, that's natural. That's geology. That's the unconformity of consciousness, where not every moment need be preserved, where forgetting is part of the cycle, where rest means letting some things simply wash away. Let the folds and faults and gaps in stone teach you, everything bends, everything breaks, everything is renewed. Slowly. Patiently. Inevitably. Deep beneath the surface, far below the reach of weathering and erosion, far below even the depth where new sediments form, there exists a realm of transformation. Here, in the middle and lower crust, pressure and temperature create a quiet magic. They turn one kind of rock into another entirely, without ever melting it, through a process called metamorphism. And there's perhaps no gentler story in all of geology than this tale of stones transformed by nothing more than patient warmth and steady weight. Imagine a shale, a soft, fine-grained sedimentary rock formed from compressed mud. It lies buried under kilometers of other rock, the weight pressing down, the temperature rising slowly with depth. At first, nothing seems to happen. The shale remains shale. But as it sinks deeper, or as the crust around it thickens during mountain building, the conditions change. At temperatures around 200 degrees Celsius and pressures equivalent to several kilometers of overlying rock, the minerals in the shale begin to reorganize themselves. No melting occurs, the rock remains solid, but atom by atom, the minerals transform into new forms that are more stable under these conditions. The shale becomes slate, its clay minerals recrystallizing into tiny mica flakes aligned parallel to each other, giving the rock its characteristic property of splitting into smooth, flat sheets. But the transformation doesn't stop there. If the temperature continues to rise and the pressure continues to build, perhaps the rock is being buried even deeper, or perhaps it's being compressed in the heart of a growing mountain range. The slate transforms again. The mica crystals grow larger, still aligned, and the rock becomes phyllite, with a subtle sheen on its surface from the larger mica flakes. Still deeper, still warmer, and phyllite becomes schist, or rock where the mica crystals are now large enough to see easily, giving the stone a glittering, layered appearance. And at the deepest levels, under the greatest pressure and heat, schist can transform into gneiss, pronounced gneiss, a beautifully banded rock where minerals have segregated into alternating light and dark layers, a stone that almost looks like it's been painted with broad brushstrokes of white and black. This sequence, shale to slate to phyllite to schist to gneiss, can take 100 million years or more. Each transformation happens so gradually that if you could watch a single crystal, you'd see nothing change in your lifetime or in 1,000 lifetimes. Yet the change is happening, molecule by molecule, driven by nothing more than warmth and weight, the same forces that create diamonds from carbon and rubies from aluminum oxide. Time and pressure, working together, create beauty from mud. What makes metamorphism so profoundly peaceful to contemplate is this: it happens in the solid state. The rock never melts, never becomes fluid. Instead, it simply rearranges itself from within, finding a new configuration that suits its circumstances. It's adaptation in its purest form, not resistance, not struggle, but transformation. The rock accepts its new depth, its new temperature, its new pressure, and becomes something more suited to those conditions. There's wisdom in this, don't you think? The ability to remain solid, remain yourself, while still transforming to meet the conditions you find yourself in. Consider marble, that elegant stone of sculptures and architecture. Marble is metamorphosed limestone. The calcite crystals that made up the original limestone, perhaps formed from shells on an ancient seabed, recrystallize under heat and pressure into larger, interlocking crystals that give marble its characteristic appearance and its ability to take a high polish. Michelangelo carved David from marble quarried in the Apuan Alps of Tuscany, marble that had once been limestone deposited in a shallow tropical sea, then buried, heated, transformed, uplifted, and exposed. The stone he carved had been on a journey of hundreds of millions of years, through the sea floor, through the depths, through mountain building, just to reach his hands. Every sculpture in marble is a collaboration between artist and deep time. And then there's quartzite, metamorphosed sandstone. The original sand grains were cemented together to form sandstone, but under metamorphic conditions, the boundaries between grains dissolve and the quartz recrystallizes into a mosaic of interlocking crystals. The result is one of the hardest, most durable rocks on Earth, resistant to weathering and erosion. Some quartzites are billions of years old, survivors of geological processes that would have destroyed lesser stones. They persist not through rigidity but through their ability to transform while maintaining their essential nature, still quartz, still silica, but rearranged into a stronger form. There's a particular type of metamorphism that happens along fault zones, where rocks grind past each other. The friction and pressure in these zones creates a rock called millenite, where the mineral grains have been stretched and flattened into long, flowing shapes that wrap around each other like taffy. Looking at a thin slice of millenite under a microscope is like looking at frozen flow. You can see that the rock was moving, deforming, streaming past itself, yet it never lost its solidity. It's a record of motion and stability existing together, of change and persistence as one. Let this thought settle over you now. Transformation doesn't require destruction. You don't need to melt down and start over. Sometimes change happens while you remain whole, while you remain yourself, simply rearranging your inner structure to better suit where you find yourself. The pressure you feel, the heat of stress, these aren't destroying you. They're potentially transforming you into something stronger, something more beautiful, something more stable under the conditions of your life. Like shale becoming schist, like limestone becoming marble, you can change while remaining solid. Picture the darkness deep in the crust where these transformations happen. No light has ever reached there. No eyes have ever seen these processes occurring. Yet in that darkness, in that solitude, under that pressure, some of Earth's most beautiful stones are born. Your own dark moments, your own pressure, your own depth, perhaps they too are creating something beautiful that you simply can't see yet. Something that will only be revealed when you rise again to the surface, when the overlying rock erodes away, when your transformation is finally exposed to light. Rest in this knowledge. Let the pressure of the day settle around you, not as a burden, but as the beginning of transformation. Let the warmth of your bed be the gentle heat that allows your internal structures to shift and find new arrangements. Let yourself crystallize slowly into the person you're becoming. You are metamorphic. You are changing. You are becoming something beautiful in the darkness. Now let's rise back to the surface and meet geology's gentlest workers: water, ice, and wind. These are the sculptors of landscapes, the patient artists who carve mountains into valleys, who shape coastlines and polish stone, who work not in sudden violence but in the accumulation of countless small actions over vast stretches of time. And in their work, we find perhaps the most accessible lesson about the power of persistence. Begin with water, the most tireless sculptor of all. Every raindrop that falls begins a journey. Some water evaporates back into the sky, but much of it flows downhill, joining with other drops, forming rivulets, then streams, then rivers. And as water flows, it carries with it particles of rock, sand grains, silt, dissolved minerals. This is erosion in its most fundamental form, and it happens everywhere, all the time, in quantities so small that you'd never notice in a single day, yet in volumes so immense over geological time that they reshape entire continents. Consider the Grand Canyon, that magnificent testament to patient erosion. The Colorado River has been carving through the rock layers of the Colorado Plateau for roughly 5 to 6 million years. The canyon is now over a mile deep in places, exposing rock layers that span nearly 2 billion years of Earth's history. But here's what makes this so beautifully restful to contemplate: the river didn't excavate this canyon through force or fury. It simply flowed, day after day, year after year, millennium after millennium, carrying away particles of rock grain by grain. The river removed the canyon more than it carved it, dissolved it, abraded it, lifted it away suspended in water and carried it downstream to the sea. 5 million years of patient removal, of gentle persistence, created one of Earth's most dramatic landscapes. The layers exposed in the Grand Canyon walls tell their own soothing story. At the bottom lie the Vishnu schist and Zoroaster granite, metamorphic and igneous rocks nearly 2 billion years old, the twisted, contorted remains of an ancient mountain range. Above these sits the Great Unconformity, a gap representing hundreds of millions of years when rock either wasn't deposited or was deposited and then eroded away. Then come the sedimentary layers, the Tapeats sandstone, the Bright Angel shale, the Mauve limestone, each representing an ancient environment, an ancient sea that once covered this region. Higher still, more layers, each with its own color, its own texture, its own story of deposition. And the river simply revealed them all, patiently removing what lay above to expose what lay below, like turning pages in the slowest book ever written. Rivers shape more than canyons. Every meandering stream, every winding river, creates its curves through a process of such elegant simplicity that it feels almost intentional. Water flows faster on the outside of a bend and slower on the inside. The faster water erodes the outer bank, while the slower water deposits sediment on the inner bank. This causes the bend to migrate slowly sideways, the river carving away at one side while building up the other. Over centuries and millennia, rivers swing back and forth across their floodplains like slow pendulums, creating sweeping curves called meanders. Sometimes a meander becomes so exaggerated that the river cuts through the narrow neck of land separating one bend from another, abandoning the old curve and leaving behind a crescent-shaped lake called an oxbow lake. The old channel remains, a quiet pool beside the active river, a memory of where the water used to flow. Everything changes. Even the paths of rivers are temporary. But the change is so gradual that the landscape has time to adjust, time to accommodate, time to prepare. Now picture glaciers, rivers of ice that flow even more slowly than rivers of water. In places where more snow falls in winter than melts in summer, the snow accumulates year after year, compacting under its own weight into ice. When the ice grows thick enough, typically at least 30 or 40 meters, it begins to flow downhill under the influence of gravity, moving perhaps a few centimeters per day, perhaps a few meters per year, grinding slowly over the bedrock beneath. This is a glacier, and it is one of nature's most powerful sculptors, yet it works with the patience of stone itself. During the Ice Ages, periods when Earth's climate cooled enough for vast ice sheets to spread across continents, glaciers covered much of North America and Europe. The most recent ice age reached its maximum extent only about 20,000 years ago, recent enough that the landscapes carved by those glaciers are still fresh, still recognizable. In places like Yosemite Valley in California, glaciers flowing down from the Sierra Nevada carved U-shaped valleys with steep walls and flat floors, polishing the granite into smooth curves and leaving behind hanging valleys where tributary glaciers once joined the main ice stream. When the glaciers finally retreated as the climate warmed, waterfalls tumbled from these hanging valleys, Bridal Veil Fall, Yosemite Falls, water now flowing where ice once crept. The Great Lakes of North America are scars left by glaciers, depressions scoured into the bedrock by ice sheets thousands of meters thick, now filled with water. The rocky, lake-studded landscapes of Canada and Scandinavia, the thousands upon thousands of lakes that these regions, are almost all glacial in origin, carved by ice or formed in depressions left when the ice melted. Even the gentle rolling hills of much of the northern United States and Europe are glacial features, moraines, accumulations of rock and sediment pushed along by advancing glaciers and left behind when they retreated, like titolines marking where the ice once stood. What's profoundly peaceful about glaciers is their rhythm. They advance when the climate cools, retreat when it warms. They flow, they pause, they melt, they reform. During the Pleistocene epoch, the ice sheets advanced and retreated dozens of times, each glaciation lasting tens of thousands of years, each warm period between lasting thousands more. The ice came, shaped the land, and retreated, over and over, each time recarving the same valleys slightly differently, polishing the same bedrock a bit more. It's the rhythm of breath, expansion and contraction, advance and retreat, but measured in millennia instead of seconds. Even wind, the lightest of the sculptors, shapes stone given enough time. In deserts where vegetation is sparse and rock is exposed, wind carrying sand grains acts like a sandblaster, slowly abrading rock surfaces, polishing them, carving them into fantastic shapes. The great arches of Utah, delicate arch, landscape arch, double arch, were shaped primarily by water and frost, yes, but wind played its role too, polishing, refining, removing grain by grain. Some of these arches are so delicate now, so thin in places, that they seem impossible, yet they've stood for thousands of years and will stand for thousands more before finally, inevitably, they collapse. Even their collapse will be gentle, geologically speaking, a slow weakening, a gradual thinning, until one day gravity finally wins and the stone settles into a new configuration. Nothing is permanent. Even arches fall. But they stand for so long, grace the landscape for so many generations, that their eventual fall feels less like tragedy and more like completion. Let yourself think now about the accumulation of small actions. A river removes a grain of sand. Then another. Then another. Over 5 million years, a canyon a mile deep. A glacier advances a few meters. Then a few more. Over 20,000 years, the Great Lakes. Wind lifts a particle of dust. Then another. Over millennia, polished stone. Everything that seems immovable was shaped by small, persistent actions. Everything that seems permanent is slowly changing. Your own small actions, the kindnesses, the efforts, the daily choices, they too accumulate. They too shape landscapes, though you may not see the canyon forming, may not recognize the valley being carved. Trust and persistence. Trust and patience. Trust that small actions, repeated with the constancy of flowing water, will eventually move mountains. Let the rivers flow through your mind now, carrying away the sediment of worry. Let the glaciers of sleep advance slowly over your thoughts, smoothing them, reshaping them. Let the wind of your breath polish away the rough edges of the day. You are being sculpted. Gently. Patiently. Beautifully. We've spoken of rocks forming, transforming, and eroding as if they exist in isolation, but now let's discover one of geology's most quietly beautiful secrets: rock and life are partners. They shape each other, depend on each other, create each other in ways so intimate and so patient that they blur the boundary between the living and the geological. And in this partnership, we find a story of collaboration that has been unfolding for billions of years. Begin with soil, that thin skin covering much of the land surface. Soil seems humble, ordinary, easy to overlook. But soil is where geology and biology meet and merge. It forms through a process called weathering, where rock is broken down into smaller and smaller particles, but this isn't purely a physical or chemical process. Life itself is one of the primary agents breaking down rock. Lichens, those crusty patches of color you see on boulders and stone walls, are composite organisms, part fungus and part algae or cyanobacteria, living in symbiosis. They colonize bare rock and secrete mild acids that slowly dissolve the stone's surface, extracting nutrients they need to survive. In doing so, they create tiny pockets where moisture can collect and where other organisms can eventually take hold. As lichens spread and die, their remains mix with rock particles to create the first primitive soil. Mosses arrive next, their roots, tiny thread-like structures, working into cracks, expanding them slightly. When the moss dies, it adds more organic matter to the developing soil. Eventually, the soil becomes deep enough for small plants, then larger ones, each generation's roots penetrating deeper, each plant's death adding more organic material. A mature soil might take 10,000 years to develop just 30 centimeters of depth. 10,000 years for 1 foot of the earth beneath a forest. Every garden, every farm field, every grassland sits atop millennia of patient collaboration between stone and life. But life doesn't just break down rock, it also creates it. Remember those limestone cliffs we spoke of earlier, formed from the accumulated shells of marine organisms? That's life building stone. For billions of years, countless organisms have extracted dissolved calcium and carbonate from seawater and used it to build shells, skeletons, and protective structures. When these organisms die, their hard parts accumulate on the seafloor. Over time, this biogenic sediment created by living things, compacts and cements into limestone. Vast portions of the Earth's crust are essentially fossil graveyards, the compressed and lithified remains of ancient life. The white cliffs of Dover that we mentioned before, those aren't just rock. They're trillions of tiny lives, transformed into stone, enduring far longer in death than they ever did in life. Some of the most extensive rock formations on Earth are reefs, built by coral polyps no larger than your fingernail. Each tiny polyp secretes a calcium carbonate skeleton. The polyp lives in a thin layer of tissue on the surface of this skeleton, building upward, building outward, generation after generation. A single coral colony might live for hundreds of years, growing just a few centimeters per year. A coral reef, like the Great Barrier Reef stretching over 2,300 kilometers along Australia's coast, represents thousands of years of continuous construction by billions upon billions of these tiny architects. The reef is both living and stone, the surface is alive, a thin veneer of polyps and algae and fish and countless other organisms, while beneath lies the accumulated skeleton of millennia, solid limestone created entirely by life. What makes this so beautifully restful is the patience involved. A coral polyp doesn't know it's building a reef. It simply lives, secretes its skeleton, reproduces, and dies. Yet the accumulation of these individual lives, none of them trying to build anything grand, creates structures so massive they can be seen from space, structures that provide habitat for thousands of other species, structures that protect coastlines from storms. Purpose doesn't require intention. Meaning emerges from persistence. Grand outcomes arise from simple actions repeated faithfully over time. Life has even shaped the atmosphere itself through geological processes. Billions of years ago, Earth's atmosphere contained almost no oxygen. The early atmosphere was rich in carbon dioxide, methane, and nitrogen, but free oxygen was vanishingly rare. Then, about 2.4 billion years ago, something remarkable happened, an event geologists call the Great Oxidation Event. Cyanobacteria, tiny photosynthetic organisms living in shallow seas, had been slowly producing oxygen as a waste product of photosynthesis for hundreds of millions of years. At first, this oxygen was immediately consumed by chemical reactions with iron dissolved in the ocean, creating vast deposits of banded iron formations, alternating layers of iron oxide and silica that settled to the seafloor. These formations, found on every continent, represent the rust of an entire ocean, oxygen combining with dissolved iron and precipitating out as solid rock. But eventually, the ocean ran out of dissolved iron to oxidize. The oxygen produced by cyanobacteria began to accumulate in the atmosphere instead. Over millions of years, the atmosphere transformed from oxygen-free to oxygen-rich. This was catastrophic for many forms of life that had evolved in the oxygen-free environment. Oxygen was toxic to them, and many went extinct. But this catastrophe opened the door for new forms of life that could use oxygen for respiration, eventually leading to all the complex oxygen-breathing life we see today, including us. The air you're breathing right now exists because of microscopic organisms that lived billions of years ago, patiently photosynthesizing, generation after generation, slowly rusting the ocean and eventually transforming the sky. Every breath you take connects you to that ancient, patient work. Even the rocks beneath the ocean floor are alive, in a sense. Scientists have discovered microbes living in the pores of oceanic basalt, kilometers beneath the seafloor, in conditions of complete darkness, high pressure, and limited nutrients. These organisms grow incredibly slowly. Some may divide only once per 1,000 years, but they're there, extracting energy from chemical reactions with the rock itself, quietly existing in one of Earth's most extreme environments. The boundary between geology and biology blurs here. Are these microbes living in rock, or are they part of the rock? Are they inhabitants of the subsurface, or are they an integral component of it? Consider too the process of petroleum formation, another intimate partnership between life and geology. Ancient marine organisms, primarily microscopic algae and plankton, lived, died, and settled to the seafloor in environments where oxygen was scarce. Without oxygen to decompose them fully, their organic remains were buried under accumulating sediment. Over millions of years, as the sediment turned to rock and was buried deeper, the organic matter was subjected to increasing heat and pressure. At temperatures around 60 to 120 degrees Celsius, the complex organic molecules broke down into simpler hydrocarbons, oil and natural gas. The petroleum we extract from the earth is fossil sunlight, ancient photosynthesis, life from hundreds of millions of years ago transformed by geological processes into liquid and gas. Every time you see a car driving, a plane flying, or a plastic object, you're witnessing a partnership between Jurassic plankton and geological heat, between life and stone. There's a kind of peace in recognizing how thoroughly intertwined life and geology are. We tend to think of rocks as dead, inert, separate from the living world. But they're not. They're partners in the great cycle. Life builds rock. Rock weathers into soil that nurtures life. Life transforms the atmosphere. The atmosphere alters weathering patterns. Everything connects. Everything collaborates. Nothing exists in isolation. As you settle deeper into rest now, think of yourself as part of this ancient partnership. The minerals in your body, calcium in your bones, iron in your blood, phosphorus in your DNA, were once part of rock, were weathered and dissolved and taken up by plants, eaten and absorbed and incorporated into living tissue, passed from organism to organism until they reached you. You are made of stone and water and ancient sunlight, temporarily assembled into consciousness. And one day, those minerals will return to the earth, will become part of the soil, will be taken up by new life or washed to the sea or incorporated into new rock. The atoms that make you are older than the mountains and will outlast them. You are geology that learned to think, stone that learned to wonder. Rest in this knowledge. You are part of the long, slow partnership between life and stone. You are both the living and the enduring. You are both the temporary and the eternal. Let yourself settle like sediment. Let yourself become part of the bedrock of sleep. Now we arrive at one of geology's most tender gifts, the preservation of moments. Not just any moments, but fragments of ancient life, ancient environments, ancient days frozen in stone. These are fossils, and they are geology's way of remembering. In the patient keeping of these memories, we find a story about impermanence and preservation, about loss and discovery, about how even the most fragile things can endure if the conditions are just right. Most living things, when they die, simply disappear. They decay, are scattered by scavengers, are broken down by bacteria and return to the soil. This is the natural way, the cycle of nutrients, and it happens to more than 99% of all organisms that have ever lived. But occasionally, very occasionally, an organism dies in just the right place, in just the right way, and instead of vanishing, it is preserved. Perhaps it falls into a quiet lagoon where oxygen is scarce and decomposers can't thrive. Perhaps it's quickly buried by a sudden influx of sediment. Perhaps it's trapped in tree resin that will become amber, or frozen in permafrost, or buried in volcanic ash. And then, over enormous spans of time, the remains are transformed into stone, becoming part of the rock record. They become fossils. The most common fossils are shells and bones, the hard parts of organisms, the parts that resist decay. When a marine animal with a shell dies and settles to the seafloor, its soft tissues decay away, but the shell remains. Sediment buries it. More sediment accumulates above. The weight compresses the layers. Mineral-rich water percolates through the sediment, and gradually, the minerals in the shell may be replaced by other minerals from the surrounding water, or the space where the shell was may fill with minerals, creating a perfect stone replica of the original. This process, called permineralization or replacement, can preserve details so fine that scientists can see the growth lines in ancient shells, can count the rings like counting years in a tree. But sometimes, under special conditions, even soft tissues can be fossilized. In the Burgess Shale of British Columbia, a deposit about 508 million years old, a sudden underwater mudslide buried a community of marine organisms so quickly and completely that even animals without shells or bones were preserved. Creatures that normally would have left no trace in the fossil record were pressed into the fine mud like prints in clay. When paleontologists split the shale today, they find the outlines of jellyfish, the delicate legs of arthropods, the soft bodies of worms, organisms so fragile that it seems miraculous they could last 500 million years. Yet here they are, testimony to a single catastrophic day in the Cambrian Sea, when the mud came down and covered everything, creating darkness that paradoxically became a kind of immortality. There's something profoundly moving about fossils when you consider what they represent. Each one is an individual organism that once lived, breathed, ate, perhaps struggled, perhaps thrived. A trilobite fossil, for instance, those segmented arthropods with their distinctive three-lobed bodies, represents a creature that crawled across a seafloor perhaps 400 million years ago. It molted as it grew, leaving behind its old exoskeleton. It sensed its environment through compound eyes. It was alive in every sense that matters. And then it died, and by sheer chance, by an improbable combination of circumstances, its remains were preserved. Out of billions of trilobites that lived and died, we have fossils of perhaps a tiny fraction. Each fossil is a lottery winner, one of the vanishingly rare individuals whose death became permanent memory. Petrified wood offers another kind of preservation, and another lesson in patience. When a tree dies and falls into water or is buried by volcanic ash or sediment, its wood can be infiltrated by mineral-rich water. Over millions of years, the organic molecules of the wood are gradually replaced by minerals, usually silica, the same material that makes up quartz, while maintaining the original structure of the wood. The result is stone that looks exactly like wood, preserving not just the shape of the tree but the growth rings, the cellular structure, even the texture of the bark. In Petrified Forest National Park in Arizona, entire fossil logs lie scattered across the landscape, their surfaces showing swirls of color, reds, yellows, blues, from different minerals that replaced the original wood. These trees fell in a tropical forest about 225 million years ago, long before the first flowers bloomed, long before grass existed, long before the first bird took flight. They were buried, transformed molecule by molecule into stone, and then exposed again by erosion millions of years later. They are the same trees, yet completely different, wood become stone, organic become mineral, yet still recognizably themselves. Fossils are time machines, but gentle ones. They don't transport us violently to the past, they simply allow the past to quietly persist into the present. When you hold a fossil, you're holding deep time in your hand. The ammonite shell, spiraled and perfect, was part of a living animal swimming in Mesozoic seas. The fern frond pressed into coal was green once, photosynthesizing in a carboniferous swamp. The dinosaur bone, massive and dense, supported the weight of an animal that felt the sun on its scales, that heard the wind in ancient conifers, that existed in a world as real and vivid as ours, just unimaginably distant. And fossils tell us not just about individual organisms but about entire vanished worlds. The coal deposits that fuel power plants and once powered the Industrial Revolution are compressed forests from the Carboniferous period, roughly 300 million years ago. During this time, vast swamps covered much of the land, dominated by giant tree ferns, club mosses, and horsetails that grew to enormous sizes. When these plants died, they fell into the oxygen-poor swamp water where they didn't fully decay. Instead, they accumulated, layer upon layer, eventually being buried and compressed into peat, then lignite, then coal. Each seam of coal represents a forest, or many forests, thousands of years of plant growth compressed into a layer perhaps a few meters thick. When we burn coal, we're releasing the energy of ancient sunlight captured by plants that grew before reptiles ruled the earth. Trace fossils offer yet another kind of memory, not the organism itself, but evidence of its behavior. These are fossilized footprints, burrows, tracks, nests, even fossilized feces called coprolites. In some locations, you can see dinosaur footprints preserved in what was once mud, now hardened into stone. Each footprint records a moment, a dinosaur stepping, its weight pressing into soft sediment. Perhaps it was walking to water. Perhaps it was fleeing a predator. Perhaps it was simply crossing this spot on an ordinary day that, by sheer chance, became extraordinary through preservation. The animal walked on, lived its life, died, and vanished, but this single step remained, became stone, endured for hundreds of millions of years. There are trackways where you can see multiple dinosaurs traveling together, their footprints overlapping in parallel, suggesting herding behavior. There are places where you can see where a predator's tracks intersect with a prey animal's tracks, a chase preserved in stone, the outcome unknown but imagined. These aren't just fossils, they're frozen stories, narratives in stone, tales with no ending because the next moment washed away or wasn't preserved. They're reminders that every moment is unique, that even the mundane can become precious given enough time, that a simple walk across mud can, under the right circumstances, outlast mountains. Let this thought comfort you: the universe has a way of preserving what matters, even if we can't always predict what will endure. Some moments vanish completely, and that's natural. But some moments, some gestures, some creations persist far longer than we imagine. A kind word might be forgotten by tomorrow, or it might echo through someone's life for decades. A small action might dissolve into the general background, or it might become, metaphorically, a fossil, a trace that endures, that shapes what comes after, that provides evidence to future moments that this happened, that you were here. You don't need to be extraordinary to leave a trace. the most common fossils are of ordinary organisms doing ordinary things. Living, eating, existing. Your existence itself is significant. Your presence makes impressions, leaves traces, matters in ways you can't fully see. Not everything needs to be preserved to have value, but know that you are creating traces simply by being, simply by moving through your days, simply by existing in this particular moment of deep time. As sleep approaches, imagine yourself settling into sediment. Your thoughts, your memories of today, gently being compressed, slowly being transformed. Some will fade, that's natural, that's the way of things. But some will be preserved, will become part of the permanent record of who you are, will endure as the foundation upon which tomorrow is built. Trust the process of preservation and decay. Both are necessary. Both are natural. Both are part of the long, slow accumulation of a life. You are both the fossil and the sediment surrounding it. You are both the memory and the keeper of memory. You are both the moment and its preservation. Rest now, and let yourself be gently held by time, the way stone holds the imprint of ancient ferns, the way amber preserves the form of ancient insects, the way the earth keeps its memories safe in the patient darkness underground. As we near the end of our first journey through geological time, let's return to where we began and discover the most peaceful truth of all, that everything in geology is a circle, a cycle, an eternal return. Nothing is truly created, nothing is truly destroyed. Everything simply changes form, moves through phases, and comes around again. And in this endless cycling, there is profound comfort. We've traveled together through the rock cycle, from molten magma cooling into igneous rock, to weathering and erosion creating sediment, to compression forming sedimentary rock, to heat and pressure creating metamorphic rock, to melting and returning once again to magma. But let's slow down now and truly feel the completeness of this circle, the way it ensures that nothing is ever truly lost, only transformed. A single atom of silicon, for instance, might spend 100 million years as part of a quartz crystal in a granite pluton deep underground. Eventually, tectonic forces might uplift that granite, bringing it to the surface where rain and frost begin to break it down. The crystal fractures. Our silicon atom, once locked in the heart of a crystal in the darkness, is now part of a sand grain washing down a river, tumbling with millions of other grains, slowly being rounded and polished by the endless friction of transport. This journey alone might take thousands of years as the grain works its way from mountain stream to lowland river to delta to sea. Once in the ocean, the sand grain settles to the seafloor. More sand accumulates above it. The weight builds. Minerals dissolved in seawater percolate through the spaces between grains, cementing them together. Our silicon atom is now part of sandstone, a sedimentary rock. This sandstone might lie on the ocean floor for 50 million years, slowly being buried deeper as more sediment accumulates above. The pressure increases. The temperature rises. If conditions are right, the sandstone might transform into quartzite, our silicon atom now part of a metamorphic rock, still quartz, still silica, but in a different configuration, with different crystal boundaries. But the journey doesn't end. Perhaps the quartzite is caught in a subduction zone, carried down into the mantle. At depths of 100 kilometers or more, the temperature becomes so great that the rock finally melts. Our silicon atom, after hundreds of millions of years in solid form, becomes part of molten magma once again. The magma rises, perhaps erupting at a volcano, perhaps cooling slowly underground. Our silicon atom crystallizes into a new mineral, perhaps in a new granite pluton, perhaps in a basalt flow. The cycle completes. But it's also beginning again. This is the profound truth of geology. The same atoms have been cycling through these processes for billions of years. The rocks around you, the mountains, the pebbles, the sand on a beach, are made of atoms that have likely been through the rock cycle dozens or hundreds of times. They've been igneous rock, sedimentary rock, metamorphic rock, igneous again, over and over. They've been mountains that eroded away, seafloors that subducted, magmas that cooled, again and again. The earth is constantly recycling itself, reusing its materials, ensuring that nothing is wasted, nothing is lost. And this cycling extends beyond rock. Water, too, moves through its own cycle, evaporating from oceans, condensing into clouds, falling as rain, flowing in rivers back to the sea, over and over for billions of years. The water you drink today is the same water that dinosaurs drank, that filled ancient oceans, that was frozen in glaciers, that flowed in rivers that no longer exist. It's been through countless organisms, fallen as countless rains, flowed in countless rivers. It's been everywhere, been part of everything, and it keeps returning, keeps moving, keeps cycling. Carbon cycles too, from atmospheric carbon dioxide absorbed by plants during photosynthesis, incorporated into plant tissue, eaten by animals, exhaled back as carbon dioxide, or buried and transformed into coal or oil, eventually weathered or burned and returned to the atmosphere, absorbed again by new plants, on and on. The carbon atoms in your body right now have been part of this cycle since Earth formed. They've been in rocks, in air, in ancient ferns, in trilobites, in dinosaurs, in early mammals, in countless other humans before you, and they'll be in countless beings after you. You are a temporary assembly of atoms that are themselves eternal, that will continue their journey long after you release them. There's something deeply restful about being part of a cycle rather than a linear progression. Linear things have endings, and endings can be frightening. But cycles don't end, they simply continue, phase following phase, season following season, transformation following transformation. The anxiety of finality dissolves when you recognize that you're part of something that keeps going, that nothing truly ends but only changes form and continues its journey. Think about the mountains we've discussed, those massive, seemingly permanent features of the landscape. Every mountain range currently on Earth will eventually erode away completely. The Himalayas, the Rockies, the Andes, all will one day be worn down to sea level, their rock washed grain by grain into the oceans. But this isn't a tragedy, it's simply part of the cycle. The sediment from those mountains will accumulate on seafloors, will be compressed into new sedimentary rocks, will be caught in new tectonic collisions, will be thrust up into new mountain ranges. The Himalayas will fall, but other mountains will rise, perhaps from the very sediment that once was the Himalayas. The mountains return, just in different places, different forms, different configurations. Even the continents themselves are temporary. The current arrangement of continents, Africa, Eurasia, North and South America, Antarctica, Australia, is just one frame in a very slow movie. The continents are constantly drifting, driven by the convection currents in the mantle below. In the past, they've been arranged differently. About 300 million years ago, all the continents were joined together in a single supercontinent called Pangaea. Before that, there were other configurations. And Pangaea broke apart, the pieces drifting to their current positions. But they're still drifting. In about 250 million years, scientists predict the continents will collide again, forming a new supercontinent, which has been given names like Pangaea Ultima or Amasia. Then that supercontinent will break apart, and the cycle will continue. Supercontinents assemble and disperse roughly every 500 to 700 million years. The continents breathe together and apart, in a rhythm so slow that a complete breath takes 500 million years. You can rest in this knowledge. Everything that seems solid and permanent is actually fluid over sufficient time. Everything that seems broken or scattered will eventually gather together again. Everything that seems lost is simply elsewhere, in a different form, waiting to return. The cycles are longer than you can comprehend, but they continue whether we comprehend them or not, moving with a patience that makes all human worry seem like a brief ripple on an infinite ocean. As you drift now towards sleep, imagine yourself as part of these great cycles. The atoms of your body have been cycling for billions of years and will continue for billions more. The calcium in your bones was once in ancient seas, then in limestone, then weathered and dissolved and taken up by plants and passed through the food chain to you. The iron in your blood was forged in the heart of an exploding star billions of years ago, scattered into space, incorporated into the dust cloud that formed our solar system, eventually becoming part of Earth, cycling through rocks and water and countless organisms before temporarily residing in you. You are not separate from these cycles. You are the cycles, temporarily aware of themselves. You are the Earth experiencing itself, matter that has learned to contemplate its own journey. And when you sleep, you participate in your own smaller cycle, waking and sleeping, activity and rest, tension and release, day after day, mirroring the great cycles of geology in miniature. Let yourself dissolve now into the cycle of sleep. Let the day erode away like sediment washing downstream. Let your thoughts subduct into the quiet depths of unconsciousness. Let yourself melt and cool and crystallize anew. Tomorrow you'll rise again, reformed, refreshed, part of the eternal return, the cycle continuing, the journey ongoing, nothing ended, only transformed. You are igneous and sedimentary and metamorphic. You are the mountain and the grain of sand. You are the cycle and the journey and the return. Rest now in the knowledge that the Earth has been cycling for 4.5 billion years and will continue for billions more, and you are part of that great patient turning, that endless transformation, that eternal return. Everything returns. Everything transforms. Everything continues. And you, dear traveler through deep time, you continue too. Let's begin our second journey by learning to read the Earth's diary, the layered pages of sedimentary rock that record the passage of time with more fidelity than any human chronicle. These layers, called strata, are geology's most accessible storytellers, and in their patient accumulation, we find a meditation on the nature of time itself. Imagine standing at the base of a cliff face where sedimentary layers are exposed. At the bottom, perhaps, there's a layer of red sandstone. Above it, a band of gray shale. Then limestone, cream-colored and fine-grained. Then another sandstone, this one yellowish. Layer upon layer, each with its own color, its own texture, its own character. This is what geologists call a stratigraphic sequence, and it follows a beautifully simple principle known as the law of superposition. In undisturbed layers of sedimentary rock, the oldest layers are at the bottom and the youngest are at the top. Each layer was once the surface, the seafloor, the lake bottom, the floodplain, and then it was buried by the next layer, which became the new surface, which was in turn buried by the next. The cliff face is a stack of ancient surfaces, ancient moments, ancient environments preserved one atop another. But here's where it becomes truly meditative. Each layer took time to deposit. That red sandstone at the bottom might represent a river delta that existed for 2 million years, slowly accumulating sand brought down from mountains that have since eroded away completely. The gray shale above it might represent a time when the sea level rose and the river delta was flooded, transforming into a quiet marine environment where fine clay particles settled through still water for another million years. The limestone above that might mark a time when the water became even clearer and warmer, when coral reefs grew and shells accumulated, a tropical sea persisting for 5 million years. Each layer is not just a different rock type, it's a different world, a different climate, a different ecosystem, all stacked like memories in the mind of the Earth. Geologists have learned to read these layers the way you might read tree rings or pages in a book. Certain features reveal how the sediment was deposited. Ripple marks on the surface of a sandstone layer indicate that water or wind moved across it, creating wave-like patterns that were then preserved when the next layer buried them. These ripples look exactly like the ripples you see on a beach today, except they've been frozen in stone for hundreds of millions of years. You can place your hand in the troughs between ancient ripples and know that this is exactly how the surface looked on some particular day in the Devonian period, perhaps when fish were just beginning to venture onto land, when the first forests were spreading across the continents. Mud cracks tell a different story. When you see a rock surface covered in polygonal cracks forming a pattern like dried mud, you know that this layer was once wet sediment that dried out, that the water receded or evaporated, that the mud baked in the sun until it cracked. Then water returned, and new sediment buried these cracks, preserving them perfectly. A moment of drought, frozen in time. A temporary exposure, now permanent record. Cross-bedding, those diagonal lines you sometimes see within a sandstone layer, angled in relation to the main horizontal layering, reveals that this sand was deposited by moving water or wind, that it formed dunes or ripples or bars, and the internal structure of those dunes was preserved when they were buried. The angle and direction of the crossbeds can tell geologists which way the ancient river flowed or which way the wind blew, allowing them to reconstruct the geography and climate of vanished worlds. There's something profoundly peaceful about the idea that every detail is preserved, that nothing is truly forgotten. That raindrop that fell 200 million years ago and left a tiny impression in mud, if the conditions were right, that impression might still exist, now in mudstone, a permanent record of a single raindrop in the Triassic. Most details are lost, yes, but some remain, and the fact that any remain at all is a small miracle, a testament to the Earth's patient memory. The layers also contain fossils, of course, and the fossils change from layer to layer, tracking the evolution of life through time. In older layers, you find simpler organisms. In younger layers, more complex ones. This observation led to the principle of faunal succession, the idea that fossil species appear in a recognizable order in the rock record, that each time period had its characteristic assemblage of life, and these assemblages changed over time as species evolved, went extinct, and were replaced by others. This principle allows geologists to date rocks by the fossils they contain and to correlate layers across vast distances. For instance, there's a layer found on multiple continents that contains an unusual abundance of iridium, a metal rare on Earth's surface but common in asteroids, along with shocked quartz crystals that form only under extreme pressure, and spherules of melted rock that cooled rapidly. This layer marks the end of the Cretaceous period, 66 million years ago, and it's the signature of the asteroid impact that contributed to the extinction of the dinosaurs. Below this layer, you find dinosaur fossils. Above it, you don't, except for their descendants, the birds. This single thin layer, often just a few centimeters thick, represents one of the most dramatic days in Earth's history, preserved between the ordinary accumulations of ordinary days. The catastrophe is just another layer, sandwiched between eons of normalcy. Yet even catastrophes have a strange serenity when viewed through geological time. Yes, the asteroid impact was devastating. Yes, it caused mass extinction. But life recovered. New species evolved. The layers continued to accumulate. The Earth absorbed the catastrophe and moved on, patient as always, building new ecosystems atop the ruins of old ones. The layers above the impact layer are full of life, different life, but life nonetheless, thriving, diversifying, filling the empty niches left by the extinction. Even the worst days become just another layer, buried under the accumulation of better days, until eventually they're just part of the story, no longer the ending but simply another chapter. Let yourself think about your own layers, the accumulated experiences, memories, versions of yourself stacked one atop another. The you from childhood at the bottom, buried now under years of subsequent experience. The you from last year, already becoming a lower layer as this year accumulates above it. Each version of you was once the surface, was once the present, and is now part of your personal stratigraphy. You contain all your previous selves, all your previous moments, layered and preserved, the foundation upon which the current you rests. And just as geologists can learn from each layer of rock, can understand ancient climates, ancient environments, the evolution of life, you can learn from your own layers. Your past isn't gone, it's beneath you, supporting you, providing context for who you are now. And tomorrow will add another thin layer, and the day after, and the day after, each one building upon what came before, each one eventually becoming part of the foundation for what comes next. There's no rush. Layers accumulate slowly. Some days add more than others. A storm might deposit a thick layer of sediment in hours, while calm seas might take centuries to add a few millimeters. But the overall accumulation is what matters, the patient building over time, the slow creation of something substantial from countless small additions. As you settle into sleep, imagine yourself as a layering process. Each breath adds a thin layer of calm. Each released muscle adds a layer of relaxation. Each thought that drifts away adds a layer of quiet. You're not trying to achieve sleep all at once, any more than a river delta tries to become a thick sandstone layer all at once. You're simply accumulating, moment by moment, breath by breath, layer by layer, until the accumulated weight of rest finally presses you down into the depths of sleep. Let the layers build. Let yourself be stratified into stillness. Let each moment settle atop the last until you've created, grain by grain, the perfect conditions for dreams. You are sedimentary. You are layered. You are the accumulation of countless moments, now compressed into this single, present, restful now. Now let's return to ice, but this time not as a sculptor, instead, as a calendar, a timekeeper, or recorder of Earth's climate written in frozen layers that stretch back hundreds of thousands of years. In the great ice sheets of Greenland and Antarctica, we find some of the most beautiful examples of geological patience, and in their stories, a different kind of comfort about the nature of change. Picture the interior of Greenland or Antarctica, vast, flat expanses of ice stretching to the horizon in every direction. The ice here doesn't flow dramatically like a glacier descending a mountain valley. Instead, it simply sits, accumulating snowfall year after year, century after century, millennium after millennium. Each winter, snow falls. Each summer, some of it may melt at the surface, but in the coldest regions, even summer isn't warm enough to melt the snow completely. So the winter's snow remains, and next winter adds more snow on top of it. The weight of new snow compresses the old snow beneath, slowly transforming it from fluffy crystals into dense, compact ice. This process has been happening for hundreds of thousands of years. The ice sheet on Antarctica is, in places, nearly 3 kilometers thick, almost 2 miles of accumulated snowfall, each layer representing 1 year's precipitation, compressed under the weight of all the years that came after. At the bottom of the ice sheet lies snow that fell during the last ice age, when mammoths still walked the earth, when Neanderthals lived in Europe, when modern humans were just beginning to spread across the continents. That ancient snow has been compressed into ice so dense, so old, that it holds air bubbles from an atmosphere that modern humans have never breathed. Scientists drill down into these ice sheets, extracting long cylinders of ice called ice cores. These cores are like frozen libraries. Each layer of ice contains information about the year it was deposited, what the temperature was, what the atmospheric composition was, whether there were volcanic eruptions that you're sending ash into the stratosphere, even what kinds of pollen were blowing in the wind, telling us what plants were growing in distant lands. The air bubbles trapped in the ice are time capsules, preserving samples of the ancient atmosphere. By analyzing the ratios of different isotopes of oxygen in the ice and in the air bubbles, scientists can reconstruct past temperatures and atmospheric carbon dioxide levels with remarkable precision. The deepest ice cores retrieved so far reach back about 800,000 years. That's 800,000 annual layers of snow, one stacked upon another, waiting patiently to tell their story. When scientists examine these cores, they see a pattern, a rhythm of ice ages and warm periods, cycling with regularity. About every 100,000 years, Earth's climate cools significantly, ice sheets expand across the northern hemisphere, sea levels drop as water is locked up in ice, and the planet enters what we call a glacial period. Then, over the course of about 10,000 to 15,000 years, the climate warms again, the ice sheets retreat, sea levels rise, and the planet enters an interglacial period, a warmer interval like the one we're living in now. Then the cycle repeats. Cool, warm, with a rhythm as steady as breath. This rhythm is driven largely by predictable variations in Earth's orbit and axis. The shape of Earth's orbit around the Sun changes slightly over a cycle of about 100,000 years, becoming more circular and then more elliptical. The tilt of Earth's axis changes over a 41,000-year cycle, affecting how much seasonal variation there is in sunlight. And Earth's axis wobbles like a spinning top over a 26,000-year cycle, changing which hemisphere is tilted toward the Sun during summer. These 3 cycles, called Milankovitch cycles after the mathematician who calculated them, combine to create periods when the northern hemisphere receives less summer sunlight. When this happens, winter snow doesn't fully melt in the summer, so it accumulates, and over thousands of years, ice sheets begin to grow. The ice sheets reflect sunlight, cooling the planet further, and the ice age deepens. Eventually, the orbital cycles shift again, summer sunlight increases, the ice begins to melt, and the interglacial begins. What's profoundly calming about this is the predictability. The ice ages aren't random catastrophes or divine punishments. They're the natural response to gentle, predictable variations in Earth's orbit. The planet breathes in and out, ice advancing and retreating, with a rhythm determined by celestial mechanics. It's been happening for millions of years and will continue for millions more, a slow planetary respiration that makes human concerns seem small and temporary. We are living in an interglacial period, the Holocene, which began about 11,700 years ago when the last ice age ended and the great ice sheets retreated. All of recorded human history has unfolded during this warm interval. Agriculture, cities, writing, civilization itself, all of it developed during this climatically stable period. But the ice cores tell us that this stability is itself temporary. Eventually, though perhaps not for tens of thousands of years if orbital mechanics alone were in control, the climate would cool again, and the ice would return. The ice ages are not past events, they're a recurring state that the Earth enters and exits naturally, part of the planet's normal rhythm. There's something oddly comforting about this. Even the ice ages, seemingly catastrophic from a human perspective, are just part of the cycle. They come, they go, they come again. Life adapts. Species migrate, evolve, persist. Some go extinct, but others thrive. During the last ice age, humans not only survived but spread across the globe, adapted to a stunning variety of environments, created art and culture and technology. The Ice Age was simply the world as it was, and life found its way, as life always does. The ice cores also reveal something else. They show that climate can change quite rapidly when tipping points are reached. Sometimes, within these cores, scientists find evidence of temperature shifts of several degrees occurring over just a few decades. These rapid changes are reminders that while the Earth is patient, it's also capable of quick adjustments when systems reach critical thresholds. Yet even these rapid changes are followed by new periods of stability. The climate shifts, then settles into a new pattern, then remains there for thousands of years before shifting again. Change and stability, the rhythm continuing. Think about the air you're breathing right now. Some of the molecules in each breath might have been breathed by someone living 1,000 years ago. Some might have been part of the atmosphere during the last ice age, then trapped in ice for 20,000 years, then released when that ice melted. The atmosphere mixes constantly, cycles constantly. The carbon dioxide you exhale might be absorbed tomorrow by a tree and turned into wood, or it might remain in the atmosphere for years before being dissolved in the ocean or absorbed by a plant. Everything cycles, everything mixes, everything participates in the great exchanges that keep the Earth's systems in motion. As you breathe now, slowly and deeply, preparing for sleep, think of yourself as part of this ancient rhythm of breath. The Earth has been breathing, ice advancing and retreating, for millions of years. You've been breathing, air in and out, for every moment of your life. Both rhythms are natural, both are sustaining, both connect you to something larger than yourself. Your breath is the ice age in miniature, expansion and contraction, cool and warm, intake and release, over and over, the rhythm that sustains you. Let each exhale be a glacier retreating, releasing what you no longer need, melting away the tensions of the day. Let each inhale be the gentle accumulation of snow, building peace, layer by layer, breath by breath. You don't need to force it. The ice doesn't force its cycles, it simply responds to the conditions, naturally, inevitably, patiently. The ice sheets remember 800,000 years. Your body remembers every breath you've ever taken, encoded in its rhythms, its patterns, its deep cellular knowledge of how to sustain itself. Trust that knowledge. Trust the rhythm. Trust that your body knows how to accumulate rest the way ice knows how to accumulate snow, slowly, naturally, layer upon layer, until the weight of it carries you down into deep, restorative stillness. You are cyclical. You are rhythmic. You are part of the great breathing of the planet, the expansion and contraction of ice and warmth, the eternal oscillation between waking and sleeping, between activity and rest. Let the ice age of sleep advance slowly over the landscape of your consciousness. Let the warmth of day retreat. Let the cold, quiet darkness settle in, gentle as snowfall, accumulating into something deep and sustaining and pure. Let us descend now into the realm of the smallest geological structures, minerals themselves, those ordered arrangements of atoms that form the building blocks of all rocks. In the crystal lattice, in the geometry of molecules locked in regular patterns, we find a kind of mathematical poetry, a demonstration that even at the smallest scales, the earth prefers order, symmetry, and beauty. A mineral is defined by geologists as a naturally occurring, inorganic solid with a specific chemical composition and an ordered internal structure. That last part, the ordered internal structure, is what makes minerals crystalline. The atoms within a mineral aren't randomly scattered, they're arranged in precise, repeating geometric patterns. This atomic order manifests in the external shape of crystals when they have room to grow freely. A quartz crystal, for instance, forms six-sided prisms topped with six-sided pyramids. This shape isn't arbitrary, it directly reflects the hexagonal arrangement of silicon and oxygen atoms within the crystal lattice. What's deeply meditative about crystal formation is the patience required. Crystals grow by adding atoms one at a time, or small groups of atoms at a time, to their surfaces. Each atom must find the correct position in the lattice, must fit precisely into the growing structure. This process can't be rushed. In a cooling magma chamber deep underground, a single feldspar crystal might grow over thousands of years, adding layers of atoms so slowly that the crystal has time to achieve near-perfect geometric form. The largest crystals ever found, massive selenite crystals in the Cave of Crystals in Mexico, some over 11 meters long and weighing 55 tons, grew over hundreds of thousands of years in mineral-rich water held at a steady temperature of about 50 degrees Celsius. For 500,000 years, these crystals simply grew, adding molecule after molecule, building their extraordinary size through nothing more than time and favorable conditions. There is something profoundly reassuring about crystals. They represent the universe's tendency toward order. Given the right conditions and sufficient time, chaos organizes itself into geometric perfection. Atoms that were once scattered in molten rock or dissolved in water find each other, recognize their proper positions, and lock together into patterns of exquisite regularity. It happens without intention, without effort, simply because this is the lowest energy state, the most stable configuration. The universe relaxes into beauty. Different minerals form under different conditions, and each tells a story about where and how it crystallized. Diamond, for instance, requires extraordinary pressure, pressures found only deep in the Earth's mantle, at depths of 150 kilometers or more. Carbon atoms under these extreme conditions lock together in a cubic crystal structure where each carbon atom bonds to 4 neighbors in a 3-dimensional lattice. This structure makes diamond the hardest natural material known. But diamond is only stable at high pressure. At the surface, under normal conditions, diamond is actually metastable. It wants to transform into graphite, the soft, slippery form of carbon found in pencils. But this transformation is so slow at surface temperatures that it would take millions or billions of years. So diamonds, brought to the surface rapidly by volcanic eruptions, remain diamonds, locked in their high-pressure form, patient captives of their own past. Graphite and diamond, the same element, carbon, but in completely different crystal structures, with completely different properties. One soft, one hard. One opaque, one transparent. Structure determines everything. The arrangement matters more than the composition. There's a lesson here about how the organization of components, whether atoms in a crystal or thoughts in a mind, determines the ultimate properties of the whole. The same building blocks, differently arranged, create entirely different results. Then there's calcite, the mineral that makes up limestone and marble. Calcite is calcium carbonate, the same chemical composition as the shells of marine organisms. But calcite crystals can form in dozens of different shapes: rhombohedrons, scalenohedrons, prisms, needles, all reflecting the same underlying trigonal crystal structure but expressing it in various forms depending on the conditions of growth. Calcite has another remarkable property: it's birefringent, meaning it splits light into 2 rays. If you place a clear calcite crystal, called Iceland spar, over text on a page, you'll see double images of each letter. The crystal is bending light in 2 different directions simultaneously because of its internal structure. Light passing through the ordered lattice of atoms is divided, separated, shown 2 paths through the same transparent stone. Minerals also create color through various mechanisms, and understanding these mechanisms is like learning the Earth's palette. Sometimes color comes from the main elements in the mineral. Sulfur is yellow, malachite is green from copper. Sometimes color comes from trace impurities. Pure quartz is colorless, but tiny amounts of iron create amethysts purple or citrons yellow. Sometimes color comes from defects in the crystal structure, places where atoms are missing or displaced, creating spots that absorb certain wavelengths of light. And sometimes color comes from the physical structure rather than chemistry. The play of colors in opal comes from the diffraction of light by tiny spheres of silica arranged in regular arrays, creating interference patterns that shift and shimmer as you move the stone. Every color, every property, has an explanation rooted in atomic structure and chemistry. The emerald's green, the ruby's red, the sapphire's blue, all arise from the precise arrangement of atoms and the subtle interactions between electrons and light. Beauty has a mechanism. Wonder has a structure. The aesthetic and the scientific are not separate but unified in the crystal lattice. There's a particular class of minerals called zeolites that have crystal structures full of regular cavities and channels, molecular scale tunnels running through the crystal. Water molecules and small ions can move through these channels, can be absorbed and released. Zeolites are like molecular sponges, capable of selectively filtering molecules based on size and charge. They form in volcanic rocks when hot water percolates through, dissolving some minerals and precipitating others, and over thousands of years, these intricate structures grow, creating microscopic architecture more complex than anything humans could directly build at that scale. Nature, given time, constructs molecular machinery through nothing more than patient chemistry. Consider also the perfection that crystals can achieve. In a perfect crystal, every atom is in exactly the right place, the pattern repeating flawlessly in 3 dimensions. In reality, most crystals contain defects, missing atoms, extra atoms, atoms of the wrong type, dislocations in the lattice. But given ideal conditions and enough time, crystals approach perfection. They self-correct, they anneal, they reorganize to minimize internal stress and energy. They seek perfection naturally, not through effort but through simply following the laws of physics and chemistry. They relax into their ideal form. As you relax now into sleep, think of yourself as a crystal slowly growing, slowly organizing. During waking hours, perhaps your thoughts and experiences are scattered, like atoms in solution. But as you settle into rest, into the quiet conditions of sleep, everything begins to find its proper place. Memories organize themselves. Experiences integrate. The day's chaos crystallizes into patterns, into meaning, into structure. Your mind, like a crystal, seeks order naturally when given the right conditions: stillness, darkness, time. You don't need to force this organization. You don't need to consciously arrange your thoughts like atoms in a lattice. You simply need to provide the conditions, and the organization happens on its own. Stillness. Quiet. Patience. The atoms of your consciousness will find their places, will lock into patterns, will form something ordered and beautiful from the scattered experiences of the day. Let yourself be a crystal forming. Let each breath add another layer to your growing structure. Let the geometric perfection of rest build within you, molecule by molecule, moment by moment, until you are complete, perfectly arranged, locked into the stable structure of deep sleep. You are crystalline. You are ordered. You are the universe's tendency toward beauty, toward structure, toward the peaceful geometry of atoms at rest. Deep beneath the surface, hidden from sunlight, there exist spaces carved by water, caves that wind through limestone and marble, chambers vast enough to hold cathedrals, passages so narrow you must crawl. And in these dark places, minerals create sculptures of breathtaking delicacy through processes so slow that a single formation might take 100,000 years to grow. Let us descend into these quiet chambers and discover what patient water can create in darkness. Most caves form in limestone, that sedimentary rock we've visited before, made from the compressed shells and skeletons of ancient marine life. Limestone is primarily calcium carbonate, and calcium carbonate has a particular vulnerability: it dissolves in slightly acidic water. Rainwater, as it falls through the atmosphere and percolates through soil, absorbs carbon dioxide, becoming very weakly acidic, just acidic enough to slowly dissolve limestone. Over thousands and millions of years, water seeping through cracks in limestone dissolves the rock grain by grain, molecule by molecule, enlarging the cracks into passages, the passages into rooms, creating the intricate networks we call caves. But the story doesn't end with dissolution. The same water that carved the cave also decorates it. As water drips from the cave's ceiling, it releases some of its dissolved carbon dioxide into the cave air, and when it does, it can no longer hold as much calcium carbonate in solution. The calcium carbonate precipitates out, forming a tiny ring of mineral where the water drop clung to the ceiling. The next drop adds another ring. And another. And another. Over centuries, these rings accumulate downward, building a slender tube, then a cone, hanging from the ceiling like an icicle made of stone. This is a stalactite, and it grows so slowly, typically just a few millimeters per century under most conditions, that a stalactite a meter long might be tens of thousands of years old. Some of the water doesn't precipitate its minerals on the ceiling. Instead, it drips down to the cave floor, and where it lands, it deposits calcium carbonate there as well, building upward from the floor in structures called stalagmites. Stalactites hang down from the ceiling. Stalagmites rise up from the floor. Sometimes, after millennia of growth, they meet in the middle, joining to form a column that spans from floor to ceiling, a pillar of flowstone connecting earth and sky in the darkness. There's something almost sacred about cave formations. They grow in absolute darkness, seen by no eyes, shaped by no hands, existing in their perfect forms for thousands of years before any human discovers them. They are proof that beauty doesn't require an audience, that creation happens in silence and solitude, that the universe makes art even when no one is watching. These formations exist for themselves, for their own slow process, indifferent to discovery or admiration. And the variety of formations is astonishing. There are helictites, thin, twisted stalactites that defy gravity, curving in seemingly random directions, their growth influenced by air currents and crystal structure rather than simple dripping. There are cave pearls, small, round formations created when water drips into a shallow pool and the calcium carbonate precipitates around a grain of sand or small rock, building up in concentric layers while the pearl is occasionally rolled by new drips, keeping it rounded. There are soda straws, hollow stalactites, thin as straws, through which water flows down the center before depositing its minerals at the growing tip. Some are meters long but only a few millimeters in diameter, delicate as glass, yet enduring for millennia in the still cave air. Flowstone forms where water flows in sheets across cave walls or floors rather than dripping. The minerals precipitate in rippling, curtain-like formations, frozen cascades that look like waterfalls turned to stone. And in fact, they are waterfalls in a sense, just waterfalls moving so slowly that you could watch one for your entire lifetime and never see it move, yet it's flowing nonetheless, growing, advancing, building downward at a pace measured in geological time. In some caves, in the deepest pools of still water, there are formations that look like delicate fingers or lily pads growing up from the cave floor through the water. These are called cave clouds or pool fingers, and they form when calcium carbonate-saturated water is so still, so undisturbed, that minerals precipitate directly on the water's surface, forming a delicate floating crust that eventually sinks and builds upward from the bottom. They're impossibly fragile, even a ripple in the water can destroy them, yet in the perfect stillness of certain cave pools, they persist, white and ghostly in the beam of a caver's lamp, sculptures of stillness itself. The temperature in deep caves remains constant year-round, typically matching the average annual surface temperature of the region. In the absolute darkness, in the steady temperature, in the still air that might not move for years, time itself seems to pause. These caves are among the most stable environments on Earth. While outside the seasons change, storms rage, temperatures swing from winter cold to summer heat, inside the cave, nothing changes. The temperature is the same today as it was 1,000 years ago. The humidity is constant. The darkness is absolute and eternal. In this stability, in this unchanging environment, the formations can grow undisturbed for hundreds of thousands of years. Some of the oldest cave formations have been dated to more than 1,000,000 years old. They were growing when early humans were just beginning to walk upright in Africa. They were already ancient when the last ice age began. And they're still growing now, still adding molecules to their structure, drop by patient drop, the same process continuing across eons. There's something profoundly peaceful about this continuity, this process that began before human history and will continue long after, utterly indifferent to the brief flicker of human civilization happening on the surface far above. Caves also preserve evidence of past climates in their formations. By analyzing the ratios of different oxygen isotopes in the layers of a stalagmite, scientists can reconstruct rainfall patterns from the past. Each layer represents a year or a season, and the chemical composition of that layer reflects the temperature and rainfall when it formed. Stalagmites are climate archives, growing steadily regardless of what's happening on the surface, faithfully recording conditions in their chemistry, creating libraries of climate data that stretch back hundreds of thousands of years. There's a particular cave formation that seems almost impossible when you first encounter it, anthodites, sometimes called cave flowers. These are clusters of needle-like crystals radiating outward from a central point, looking like chrysanthemums or starbursts frozen in stone. They form through a different mechanism than most cave formations, not from dripping water but from water seeping slowly through tiny pores in the rock, evaporating at the surface, and leaving behind crystals that grow outward in all directions. Each needle might be thinner than a hair but perfectly straight, perfectly formed, part of a cluster that took thousands of years to grow, a flower that will never wilt, never die, never change except to slowly grow more elaborate over the centuries. As you lie here preparing for sleep, imagine yourself in a cave, in the absolute darkness, in the perfect stillness, in the constant temperature. Nothing is demanded of you here. You don't need to move, to act, to produce. You can simply exist, like a cave formation, growing slowly, imperceptibly, adding layers of rest to your structure. Each breath is a drop of water, carrying minerals of peace, depositing them gently as you exhale. Over the course of this night, these deposits will build, will accumulate, will create formations of restoration within you. The cave formations teach us that the most beautiful things often grow in darkness, in silence, in stillness. They teach us that growth doesn't always look like growth, that sometimes development is so slow, so subtle, that it seems like nothing is happening, yet the accumulation over time creates something magnificent. They teach us that constancy matters more than intensity, that the steady drip over millennia accomplishes more than any rushing flood. Let yourself be a cave tonight, a space of perfect darkness, perfect stillness, perfect constancy. Let sleep drip into you, mineral-rich and patient, building formations of rest that will support you when morning comes. You don't need to see the growth happening. You don't need to feel each layer forming. You simply need to be still, to be dark, to be constant, and the formations will build themselves. You are a cathedral carved by time. You are stalactites and stalagmites meeting in the middle. You are beauty growing in darkness, seen by no one, existing for the pure sake of existing, perfect in your patient becoming. Let us rise now from the underground chambers and turn our attention upward, to mountains, those monuments to tectonic patience, those wrinkles in the earth's skin that take millions of years to rise and millions more to fall. In their slow ascent and slower erosion, we find perhaps geology's most visible lesson about persistence, impermanence, and the graceful acceptance of both. Mountains are not permanent fixtures. They are temporary expressions of the ongoing conversation between tectonic forces that build and erosional forces that wear down. Every mountain range on Earth is in a state of dynamic equilibrium between these opposing processes, being pushed upward by tectonic forces while simultaneously being carved away by water, ice, and wind. Some mountains are still rising, pushed up faster than erosion can wear them down. Others have stopped rising and are now in their long, slow descent back to sea level. But all mountains, eventually, will fall. Consider the Himalayas, the youngest and highest mountain range on Earth. These peaks are still rising, thrust upward by the ongoing collision between the Indian subcontinent and the Eurasian plate. India, once an island continent, has been drifting northward for tens of millions of years, and about 50 million years ago, it collided with Asia. But the collision didn't stop. India continues to push northward even now, moving about 5 centimeters per year, roughly the speed your fingernails grow, and this steady pressure crumples the crust between the two landmasses, forcing it upward into the highest peaks on Earth. Mount Everest, the highest point on the planet's surface at 8,849 meters above sea level, is still growing taller by about 4 millimeters per year. But even as Everest rises, it's being worn down. The summit is battered by winds exceeding 200 kilometers per hour. Water seeps into cracks in the rock and freezes, expanding and wedging the rock apart. Avalanches carry rock and ice downslope. Glaciers grind away at the mountain's flanks. The Himalayas are being eroded at a rate of about 2 to 12 millimeters per year, depending on location. So Everest is rising, yes, but it's also being worn away almost as fast as it rises. The mountain is like a swimmer struggling upstream, making progress, but only barely, only through constant effort against a force that never tires and will, eventually, win. Now travel in your mind to the Appalachian Mountains of eastern North America. These mountains look old, their peaks are rounded, their slopes gentler, their valleys wide and well-developed. And they are old. The Appalachians formed about 480 million years ago during a series of tectonic collisions, the same collisions that assembled the supercontinent Pangaea. At the time of their formation, they may have been as high as the Himalayas are today, perhaps even higher. Geologists have found evidence in the type of metamorphic rocks exposed in the Appalachian core, rocks that formed under pressures indicating they were once buried under 15 to 20 kilometers of overlying rock, suggesting mountains of enormous height once stood here. But for the past 200 million years, since Pangaea began to break apart and the tectonic forces stopped pushing the Appalachians upward, these mountains have been purely eroding, wearing down year by year, millennium by millennium. What we see today, peaks perhaps 2,000 meters high, are just the roots of those ancient giants, the stumps of mountains that once rivaled or exceeded Everest. Everything else, all those kilometers of rock that once towered above, has been carried away grain by grain to the sea. Entire mountain ranges worth of rock now lie as sediment on the Atlantic seafloor or have been subducted and recycled into the mantle. The mountains themselves are memories, fading slowly into flatness. And yet, the Appalachians endure. After hundreds of millions of years of erosion, they're still here, still mountains, still shaping weather patterns, still providing habitat for countless species, still rising green and forested above the surrounding lowlands. Their endurance isn't about resistance to change, it's about graceful, slow yielding. They're letting go, particle by particle, becoming smaller, gentler, more rounded with each passing epoch, but they're still present, still themselves in a fundamental way, just quieter now, more humble, no longer striving for the sky but resting into the earth. There's something profoundly moving about old mountains. They've seen so much. The Appalachians were here before the Atlantic Ocean opened. They watched Pangea assemble and then break apart. They were ancient when dinosaurs first evolved, and they watched those dinosaurs rise to dominance and then vanish. They were here for all of it, slowly eroding, slowly shrinking, but persisting, witnessing, remembering in their own way. If rocks could hold memory, these rocks would have the longest memories on any continent. The mountains teach us about the relationship between height and stability. The highest mountains are the youngest, still being actively pushed upward by tectonic forces. They're dramatic, sharp, angular, their peaks are recent work, not yet smoothed by time. But they're also, in a sense, the most precarious. They're being worn down as fast as they rise, constantly losing material to avalanches and erosion. The older mountains, lower and more rounded, have found a kind of stability through surrender. They've given up their great height but gained endurance. They're less spectacular but more stable, less dramatic but more lasting. And mountains, despite their apparent solidity, are constantly in motion in ways invisible to us. The rocks within them are under tremendous stress, compressed, bent, slowly deforming. In some cases, rocks deep within mountain ranges are flowing like extremely viscous fluids, moving centimeters per year under the pressure and heat. The mountains we see as static are actually dynamic systems, with material constantly being recycled from deep within the range to the surface through a combination of tectonic uplift and erosion. Rock is eroded from the surface, reducing the weight, allowing deeper rock to rise buoyantly, bringing buried rock back toward the surface where it too will eventually erode. The mountain is like a fountain, with material flowing upward from depth and being removed from the top, the whole system sustained by the tectonic forces that keep pushing the mountain range upward. Some mountains tell stories of even more dramatic change. In the Swiss Alps, geologists found fossils of marine organisms and rocks near the summits, evidence that these rocks, now at elevations of 3,000 or 4,000 meters, were once at the bottom of an ancient ocean. The seafloor was compressed, metamorphosed, and thrust upward during the Alpine orogeny when Africa collided with Europe. The sea became the sky. The lowest became the highest. In geology, nothing stays where it starts. Everything travels, everything transforms, everything eventually becomes its opposite given enough time. Mount Fuji in Japan, that nearly perfect volcanic cone, is only about 100,000 years old, a baby by geological standards, barely a moment in deep time. Yet it's become a sacred mountain, a symbol of beauty and permanence in Japanese culture. But geologically, Fuji is actively eroding and will eventually be worn down to a nub, and long before that, it will likely erupt again, altering its perfect form. The perfection is temporary, the beauty fleeting, not in human timescales, but in geological ones. Yet this impermanence doesn't diminish the mountain's beauty. If anything, it enhances it. The mountain is beautiful precisely because it's a moment, a particular configuration of rock and snow that exists now but won't forever. As you settle deeper into rest, think of yourself as a mountain. Perhaps during your waking hours, you strive upward, building yourself higher, pushing against resistance, achieving and accomplishing. That's the tectonic force within you, the drive to grow and rise. But now, in this time of rest, you can be like the old mountains. You can stop pushing upward and simply allow the erosion of sleep to wear away what doesn't serve you. The tensions, the worries, the sharp edges of the day, let them erode. Let them be carried away like sediment in a river, leaving behind something smoother, gentler, more peaceful. You don't need to maintain your height while you sleep. You don't need to keep pushing upward. You can settle, can compress, can allow yourself to become smaller and denser and more concentrated. Tomorrow you can rise again, but tonight, let yourself erode into softness, into rest, into the quiet stability of old mountains that have given up their great height but gained something more valuable: endurance, patience, peace. You are mountains rising and falling. You are the Himalayas striving upward and the Appalachians settling into wisdom. You are both the building and the erosion, both the height and the humility, both the sharp peaks of now and the rounded hills of eventually. Let the mountains within you settle into sleep. Let the avalanches of thought carry away what needs to go. Let the glaciers of rest grind slowly across your consciousness, smoothing everything, rounding everything, making everything gentle. Now let us travel to the driest places on earth, the deserts, where rainfall is rare and life is sparse, where the processes of geology become starkly visible because there's so little vegetation to obscure them. In the desert's bareness, in its exposure, we find clarity. And in its harshness, paradoxically, we find lessons about endurance and the subtle beauty of scarcity. Deserts form wherever the climate is too dry to support much plant life. This might be in the rain shadow of mountains, where air loses its moisture as it rises and cools, then descends dry on the other side. It might be in the subtropics, where global atmospheric circulation patterns create zones of descending, warming air that holds on to its moisture. Or it might be along cold ocean currents, where the air is cooled and loses its ability to hold water vapor before reaching land. But regardless of how they form, deserts share a common characteristic: they receive less than about 25 centimeters of rainfall per year, sometimes far less. In the Atacama Desert of Chile, some weather stations have never recorded rainfall. Not low rainfall, no rainfall, ever, in the entire history of the station. There are parts of the Atacama where no rain has fallen in recorded human history, making it the driest place on Earth. Yet even here, even in this extreme aridity, geological processes continue. They simply happen more slowly, more subtly, in ways that leave traces visible for thousands of years because there's so little water to erase them. Without abundant water to carry sediment away, desert landforms can persist for extraordinary lengths of time. Ancient shorelines from lakes that existed during wetter climatic periods millions of years ago are still visible as horizontal lines on desert hillsides, looking fresh and distinct despite their immense age. The tracks of ancient peoples, paths worn into the desert pavement by countless footsteps thousands of years ago, remain visible because there's been no erosion to erase them. In some deserts, geoglyphs, large designs made by arranging stones or removing the dark desert varnish from lighter rocks beneath, have survived for millennia, their messages or meanings long forgotten but their physical forms persisting, waiting patiently in the dry air for someone to remember or to wonder. Desert varnish itself is a beautiful mystery, one of geology's slowest paintings. This is the dark, reddish-brown or black coating that develops on rock surfaces in deserts, particularly on vertical or slightly inclined faces. It's composed primarily of manganese and iron oxides, along with clay minerals. But here's what makes it fascinating: the varnish accumulates extraordinarily slowly, typically at rates of about 1 micrometer per century, 1/1000th of a millimeter every 100 years. A coating of desert varnish just 1 millimeter thick might be 100,000 years old. Some varnish coatings in the southwestern United States have been dated to over 100,000 years, and they may be much older. How does desert varnish form? Scientists still debate the exact mechanisms, but it appears to involve microorganisms that live on rock surfaces, concentrating manganese and iron from dust particles and rainfall. These microscopic organisms, living in one of Earth's harshest environments, slowly build up layers of oxidized minerals over millennia. They're artists working on the scale of deep time, painting rocks with infinite patience, one molecule at a time, creating coatings that give desert rocks their characteristic dark, burnished appearance. And because the varnish accumulates so slowly and persists so well in the dry climate, it becomes a canvas. Ancient peoples discovered that by scraping away the dark varnish to reveal lighter rock beneath, they could create images that would last for thousands of years. Petroglyphs, rock carvings, made this way remain visible today, the dark varnish contrasting with the lighter exposed rock. The image is as clear now as when they were made. Some petroglyphs in the American Southwest are over 3,000 years old, their meanings lost to time but their forms enduring, testament to the desert's preservative power and to the human desire to leave marks, to communicate across generations, to say I was here in a way that outlasts memory. In deserts, the wind becomes a sculptor more powerful than in wetter climates. With sparse vegetation to slow it, wind can reach high speeds and carry sand grains that act as natural sandblasters, abrading rock surfaces grain by grain. This process, called abrasion, carves rocks into streamlined shapes called ventifacts, wind-carved rocks with flat faces polished smooth by millennia of sand bombardment. The faces are oriented in the direction the prevailing winds come from, creating natural wind veins that record ancient wind patterns frozen in stone. Wind also creates vast seas of sand, the classic image of deserts, though sand dunes actually cover only about 20% of Earth's desert areas. These dunes are remarkable for being both seemingly permanent and constantly in motion. The dune itself persists, maintaining its shape, but the individual sand grains are constantly moving, blown up the gentle windward slope, cascading down the steep leeward face, each grain making its slow journey across the dune's surface. Over years and decades, the entire dune migrates downwind, advancing grain by grain, while maintaining its characteristic form. A large dune might move 10 or 20 meters per year, sometimes engulfing roads, buildings, even entire oases, reclaiming them for the desert. But the movement of dunes is mesmerizing in its pattern. Watch a time-lapse of dunes migrating and you see that they behave almost like living things, like slow-motion waves crossing a solid ocean. They interact with each other, smaller dunes catch up with larger ones and merge with them, or split around obstacles and reform on the other side. They create complex patterns of ridges and troughs that shift and reorganize over time scales of decades and centuries. And yet each grain of sand is just following simple physics, being picked up by wind, carried until the wind can't support it anymore, fall into rest, then waiting to be picked up again. From these simple individual actions, complex collective patterns emerge. There's something deeply calming about sand dunes. Each grain has been on a long journey, weathered from rock, perhaps transported by rivers, deposited and then remobilized many times, slowly being rounded and reduced in size by constant collision with other grains. A single grain of sand might have been traveling for millions of years, might have been part of many different rocks, many different beaches, many different dunes. And now it rests here, momentarily, in this particular dune, before the wind picks it up again and carries it onward. In some deserts, when conditions are right, sand dunes sing. As the sand avalanches down the steep face of the dune, friction between grains creates vibrations that resonate within the dune, producing a low, booming sound that can be heard for kilometers. Different dunes produce different notes depending on the size of the grains and the moisture content of the sand. These singing sands have been reported since ancient times, described in historical accounts from the Middle East, Central Asia, and North Africa. The dunes sing their slow song, the voice of millions of grains moving together, a collective sound arising from individual motions, the desert's own music played on instruments of sand and wind. Water, when it does come to the desert, acts with sudden intensity. Desert rainstorms can drop months' worth of rainfall in a single afternoon. The ground, baked hard and lacking vegetation to slow the water, can't absorb it quickly. The water runs off in sheets, gathering into temporary streams called arroyos or wadis that flood violently for hours or days and then dry up completely. These flash floods can move enormous boulders, carve channels, reshape the landscape in hours, then vanish, leaving behind fresh deposits of sediment and a landscape scrubbed clean, exposed, waiting for the next rain that might not come for months or years. The desert teaches patience through scarcity. Life here can't afford to rush, can't afford to waste. Desert plants grow slowly, space themselves widely to reduce competition for scarce water, wait years between flowering if necessary. Some desert plants can remain dormant for years, their seeds waiting in the soil for the rare event of sufficient rainfall to trigger germination. When that rain finally comes, the desert briefly explodes into bloom, wildflowers covering the ground in a riot of color that lasts only weeks before the plants set seed and die, returning the landscape to its patient, waiting state. The bloom is spectacular precisely because it's rare, because it's a concentrated expression of life in an environment where life is usually hidden, dormant, waiting. As you lie here in the darkness, think of yourself as a desert at night. The heat and activity of the day have passed. The temperature drops. The winds calm. Everything becomes still, quiet, waiting. In this stillness, in this darkness, there's a kind of purity, a simplification. The desert at night is reduced to essentials: cool air, dark sky, silent stone. You, too, can reduce to essentials. You don't need all the thoughts that crowded your day. You don't need all the concerns about tomorrow. You can be like the desert at night, vast, quiet, simplified, essential. Let the winds of thought die down. Let the last grains of worry settle where they fall. Let the flash flood of the day's activities drain away, leaving the landscape of your mind scoured clean, exposed, bare in the most peaceful way. You are the desert's patience. You are the slow accumulation of desert varnish, building rest 1 micrometer at a time. You are sand dunes, constantly moving but never hurrying, always maintaining your essential form while yielding to the wind. In scarcity, there is clarity. In bareness, there is beauty. In the desert's patient waiting, there is wisdom.